This is AP Calculus AB, and in this video I'm going to cover the rest of section 7.4, Exponential Growth and Decay. Really what we talked about last time was just standard exponential growth and decay and some of the basic applications that we do with it. When we talk about this last topic that is part of our curriculum, which is Newton's law of cooling, it still follows the same general idea as the rest of the applications that we looked at, but it has a slightly different exponential growth model. So what we're looking at here is how long it takes for an object or some kind of a substance to heat up or cool down based on the object itself or the substance itself and the surrounding temperature. Okay, so the way this differential equation works is I want the rate of change of my temperature with respect to time. And that's equal to negative K times our temperature minus the surrounding temperature. T sub S is the surrounding temperature. Well, to solve that out, it's a little bit different algebraically, and I'm going to show you that in class, but it's fairly straightforward, but it's very slight variation from what we did before. So in the end, what we end up with here is this model. So we have our temperature minus our surrounding temperature is equal to T naught minus T sub S e to the negative KT power. And usually I write it like this. The temperature at any point in time is equal to the surrounding temperature plus the initial minus the surrounding temperature times e to the negative KT power. Sometimes you'll see it written as e to the KT power. It doesn't really make a difference when you plug everything in. That K will turn out what you need it to turn out to be, whether it needs to be positive or negative based on your equation. Okay, so let's take a look at a couple of examples. So like I said, really what we're doing here is kind of the same thing as last time, but we have a slightly different differential equation. So it says a hard-boiled egg at 98 degrees is put in a pan under running 18-degree water to cool. After 5 minutes, the egg's temperature is found to be 38 degrees. How much longer will it take the egg to reach 20? So remember, we had that setup where the temperature is equal to the surrounding temperature plus the initial minus the surrounding times e to the negative KT power. So they didn't give us all of this information, but they gave us a lot of this information. So we know the surrounding temperature is 18 degrees because that's what we're putting this hard-boiled egg under. We know the initial temperature is 98, and they gave us some information about a particular point in time. So to start with here, I know my temperature is going to be equal to 18 plus 98 minus 18 times e to the negative KT power. So I could also write that as the temperature would be equal to 18 plus 80 e to the negative KT power. And at this point, it's just an algebra problem again. So they told me that at the point of time after 5 minutes, my temperature is going to be 38. So I know 38 would be equal to 18 plus 80 e to the negative k times 5. And from that, I can solve for that K value. And the K value turns out to be approximately 0.277. And now I've got the model where I can find my temperature at any point in time. So I know it's going to be 18 plus 80 e to the negative 0.277 T power. And then they asked for how long is it going to take the egg to reach 20 degrees. All I would have to do is plug in 20 for the temperature and then solve, and it turns out that it would be 8.3 additional minutes. Now, the one thing that can be tricky about these problems is the way they word the questions. So it didn't say what's the total amount of time. It said, how much longer will it be? So when I solve this equation out, I'm actually going to get 13.3 minutes because it takes a total of 13.3 minutes. But the question said how much longer after that. So I have to subtract out that 5 minutes that already went by, and that's where the 8.3 came from. So it's a little bit tricky from the standpoint of the way the question is worded, but in the end, it's really just an algebra problem. All right, so here's another one similar to that. And what I want you to do is I want you to try this one. So it says an apple pie comes out of the oven at 425 degrees Fahrenheit, placed on a counter in a 68 degree room to cool. In 30 minutes, it is cooled to 195 degrees. According to Newton's law of cooling, how many additional minutes must pass before it cools to 100? Now, this is actually an old AP test question. So this is obviously a multiple choice. This would be on the calculator section. So what I want you to do is try to solve this one out. You can use the equation if you want, but when you get to the AP exam, you notice here they're kind of expecting you to know what Newton's law of cooling is. So last time I told you not to memorize the stuff about half-life and all of that. When it comes to Newton's law of cooling, you probably do want to have the solution to the differential equation memorized, because notice they didn't even give us the differential equation here, and we're not going to get a formula chart or anything. So you either know what it is or you don't. And in this case, if you know what it is, it's very simple. If you don't, then you're really stuck. So pause the video. When you come back, I'll show you the solution. Okay, so here's what you should have come up with. 40 minutes. Notice that this one was worded like the last one. How many additional minutes? So it's very easy to get 70 and think that's your answer. Luckily, they didn't put that as one of the choices. But the main thing is, we're starting with kind of the same idea. My temperature is equal to, and my surrounding temperature here was 68. And my initial was, oops, I need to do a plus. My initial was 425 minus my surrounding times e to the negative kt power. So using the fact that we know in 30 minutes it's cooled to 195, we can get the K value. Turns out K is about 0.03445. And then once we have that, we've got our model, and then we just plug in the temperature of 100 and solve for the time. So very, very much like the last one. It's just that I wanted you to see that this is an actual AP test question and that they do expect you to know Newton's law of cooling. So that is something you're going to need to memorize. Now, I did put a little bit more in these notes. I put something in here about logistic growth. This is actually beyond the scope of this course. And the reason it's beyond the scope of this course is because it uses a little bit different differential equation that requires you to know how to integrate using partial fractions. That's not a topic for this class. It's a topic for BC calculus. But I thought it was an interesting application for you to see, because a logistic growth model you'll see a lot of times in biology or things like that. It's a population model that is kind of more realistic in the long term, because what will happen is early on in your model, your population grows very quickly, and then your population growth will start to flatten out. And the reason that your growth rate will flatten out is because there's limiting factors to population growth. There can be overpopulation for many reasons. You can have too many people in a small place, or too many animals in a small place, or whatever it is. There can be not enough food, not enough water, whatever it happens to be. There's natural values that the population is going to want to approach. And so this value that you see right here, that is called our carrying capacity. So our population is always going to want to approach that carrying capacity. So it'll start out, if we start out low enough, our population will start out growing very much like an exponential growth model. And then at some point, it'll start to flatten out as we approach that carrying capacity. So like I said, not something you have to know, but something interesting to look at if you wanted to see some applications of exponential equations and differential equations beyond just what we have done. Okay, so I also attached a worksheet here. So this worksheet is not required, but I put it in here because I wanted you to see the types of questions I'm going to expect you to know how to do. So you do have the assignment in Math Excel that's got some application questions in there, but I wanted you to see specifically, what you might see on a quiz, on a test, how the questions are going to be worded, what's the difficulty level, just so you had kind of a better feel for that. So I put all of these questions here, and I've got the solutions for these posted on the Schoology page so that you can try them out. You don't necessarily need to work through all of them, but you might want to try a couple of them and just see if you can work through them. Now, there are a couple that I put in here that deal with logistic growth model. It's not something you have to know how to do. In fact, this one right here, number 8, has to do with the logistic growth model. You don't have to do that one. But again, if you're interested, you can check that one out. Okay, so that's really everything in section 7.4. So at this point, you should be able to finish that entire assignment in Math Excel. And like I said, just use this worksheet to supplement if you feel like you need extra practice.